Right, let's build some collision layer for these guys. So I'm gonna drop down agent collision layer, and I'm just gonna build one side so you don't have to see me do everything. But here you see I get the dots I had before. Let's start with the head. And for the head, the default is always a capsule, and usually I use a capsule, but sometimes it's actually better to use a box, I found. It depends on the rigs. You will see that with different rigs you need to do different tweaks. And for this rig I think it works well with the capsules, but when you have a rig with a very wobbly head, if you put a box instead, it tends to just like roll over to one side and lay there flat, and then you get better motion. So that's the first thing. And then for the neck, usually I don't put anything on the neck, but there are actually rigs when I put something in the neck. And the reason when I put something on the neck, that is usually because I want to separate two cone twist constraints. So I have one that maybe goes up and down and one that goes side to side, because I find that better to have that separated and to have the same cone twist constraint. I just find the motion gets better. But in this one I'm not even gonna bother. And the next thing I'm gonna put is I'm gonna do the chest. So I'm gonna put it here, and I'm gonna drag that out. Also capsule. Most of the capsules are great. I use them for most of the things. It's very rarely when I use custom shapes, even if I do sometimes. And also, if you press B, you have this box handle. If you press O, you have this rotation handle. So I'm gonna rotate that into place, and then I'm gonna drag the box out a little bit, and then maybe take it down a notch like that. And then I want to have the hips, and if I click on this, you will see down here that this is actually not the hips, it's the lower back to spine, and I don't want that. And if you go out to this mocap biped rig, you can see the hips are the root, and I usually want to have a collision shape on the root. But you can get that even if you can't get it in the viewport, you just need to add it by hand. So I can go in here and I can just select the hips, and now I get this red dot at the hips, and I can just press that and start to get my collision shape here. And I'm gonna rotate that actually. Rotate that up, and then I'm gonna go back to my box handle, move it down to the side, and give it some volumes. Something like this. Cool. And then let's do the arms, and they are placing it pretty well. And then I'm coming to the hand, and for the hand I need to tweak it a little bit more, rotate it into place. With the hands I tend to make them much bigger than they are, and that is just because a lot of sims, and you will see what I mean when you get there, is that you get agents laying and then the arms trying to reach the ground, and then it just gets stuck in this weird motion. So if the hands are a bit bigger, it's a bigger chance that the hand will actually reach the ground, and then that will stabilize the motion. So I tend to make them quite big. Let's go to the legs. Pretty nothing. Oh, another thing with the hand before I leave the hand. Sometimes I do boxes for hands too. For some rigs I found it better. Just to be aware of. But let's do this. And I'm gonna make this tighter. Actually I'm gonna orient that maybe a little bit. Box, back to box. And then for the feet, I don't want to have both part of the feet. It's enough to just have this guy here. And I'm gonna orient this guy up. And then I'm gonna go box, like so. And for the feet, another part where I sometimes use boxes. For this one, capsules are fine, but just to be aware of. So here, that is basically this like a rough blocking of the collision shapes. And if you want to have a blueprint, you can always check out side effects. So if I go here and look at the biped 3 and go mocap biped 3, here is there. And two things to notice, they also put their collision shapes on the hips. Another thing, they have overlapping collision geometry, and that is not a problem because the default behavior of the cone twist constraints are that they are not colliding with the shapes they are attached to. So these two shapes won't collide with each other. So, right. But yes. So let's move on to the actual join constraints. Alright, so I actually added some clip properties and set up the foot locking, and also made these guys use the locomotion instead, just to make it look a little bit nicer. But what I also did is I added this little cannon here. So first thing I want to do is I want to add some tracer fire to this. Let's first go into the gun. So what I'm going to do, I'm going to do some particles that gets shot out from this cannon. And if we look at the cannon here, I'm going to make one of the polygons here an emitter. To do that, I'm going to drop down a group. I'm going to call this emitter. And then I'm going to click this little arrow here. And then I'm going to select this little polygon here. And enter. Well, the next thing I'm going to do is to create a geometry for the tracer fire. Tracer fire. And let's go in here. Now I want this emitter, so I'm gonna do an object merge. And let's hide everything. And I'm gonna import this cannon. So I'm gonna go to this out cannon. So now I have the cannon, and now I just want to blast away everything except the emitter. So I'm gonna drop down a blast here. Gonna select the group emitter, and then I'm gonna select this delete non-selected. So now I have this geometry that is following the cannon. Cool. Now I'm gonna drop down a dub sim, and I'm gonna connect this to the first port here. And let's go in here, and I'm gonna drop down a pop solver, and then I'm gonna drop down a pop object. It's quite similar to the crowd solver. Instead of a crowd solver, you have this pop solver, because we're just gonna deal with points here. And instead of the crowd object, we have a pop object. And now, as you might have guessed, we're going to have a pop source instead of a crowd source. Let's connect that to the second one here. And then for this emission type, scatter on surface is perfect. Geometry source, first context geometry. And now we can see that it is emitting, but the particles aren't moving at all. So we need to give them some velocity. To decide what velocity we're going to have, I'm actually going to use the normal from this primitive. So first I'm going to make sure that I have a normal on the primitive, so I'm going to drop down a normal here. And now we're going to have a primitive. And then I'm going to drop down a wrangle here. And I'm going to set at v. And v then is velocity. And I don't need to tell Houdini that this is a vector, because this is a known attribute. I'm going to set the velocity is equal to the normal. And the same thing with the normal here. You can see that immediately something happened. You can see they popped up a little bit. And that is just because by default this pop source in attributes use inherited velocity. And as I just set the velocity on the emitter to the normal, the particles will travel in that direction. But I want them to be a bit faster. So let's put this up to 50. So now it's a little bit faster. And I'm also going to do two other things. One thing is that I don't want this many particles. I maybe want 10. Another thing is the first frame is so far off from the cannon already. What I can do then is to use this jitter birth time to have the particles get a random age within the current time step, and in that way not have them all start at the same position. And then you see that is getting closer to the cannon here. This is a little bit better. Cool. Right, so let's go out again. So I don't just want it to be point. Let's see here are the zombies. I'm gonna make something more tracer fire like, so let's drop down a copy to point. And then I'm also gonna drop down a tube. And I can see I'm copying tubes, but maybe not like how we wanted to copy them. First of all, let's put down a transform. I'm just gonna rotate this tube here to 90. So now it's pointing in the right direction. Actually, I'm gonna do minus 90. Then I'm gonna do the scale. I'm gonna take that down to here somewhere, maybe. And then I'm gonna put this to 0. And I'm also gonna put a color to this, like so. Another thing, actually I'm gonna make this a little bit bigger. So let's put this to 0.5 maybe. Something like this. And I can put on these end caps too. Otherwise it would just be hollow. And the last thing I'm going to do is I want to make these pack primitives. In the copy to points, I'm going to check this pack and instance. True. Alright, so here is our tracer fire. Okay, just one more step. So I'm going to drop down a wrangle, and the reason I'm doing this is because it's so few lines of code that I'm going to write, so it feels unnecessary to put it through an attribute swap. But anyway, let's look how we can apply force at the right place on our agent. And once again, we can do this through different agent arrays. There are a lot of agent-specific arrays that you can use. Like here you have bounce agent, density agent, force agent, friction agents, and many more. What all of these have in common is that they allow you to apply different attribute values on different transforms of an agent. If you, for example, want the head of an agent to have a different friction than the rest of the body, then you can use a function like agent rigFind to get the position the head has in all these arrays, and then set that value to whatever you want. For now we want the agent force attribute, which will allow us to apply different forces on the different parts of our agent. So I'm gonna go in here, I'm gonna do a vector and do this bracket because it's an array, and then do an attributes, force agent, like so. And if I look at this, I just have this empty array. And this is of course not what I want. I need this array to be as big as the array for the agent transforms and have a value for each transform. So what I can do then is I'm doing a resize, and then I'm using this vex function called agent transform count. So if I do an agent transform count, then it will give me the number of joints, and if I resize an array to that, then I will have a matching array. Perfect. So I do a 0 at primnum here, and then now I have this array with vectors, and the reason I need it to be vectors is that I get both a magnitude and a direction. Now we need to check if the agent got hit or not. If it got hit, then the attribute hit that we created before will be 1. Oh no, not hot. Hit. This is the same thing to say, like if hit equals to 1, then do this. But you can just do it like this instead, so if hit. And now I'm going to set something in the force agent array. But how will I know the position in the array that I'm going to set? And we know this because we saved out the rig ID in the previous lesson. The rig ID equals to the position in the array. So let's set that in here at rig ID. Now this needs to be equal to a vector that will apply the force. What direction do we want? We know that too because we set that in this hit, and that is the hit direction. But of course, as you remember, the hit direction was when it was raycasting backwards, and we want to reverse it. First of all, I'm gonna normalize it actually. And the reason I'm doing this is just because it's easier to control the magnitude of a vector. A normalized length of 1 multiplied with another float will have the magnitude of that float. So in this case, I'm gonna do add hit dir, normalize that, and I'm multiply minus because I'm going to reverse it, and I'm just going to put 2000 here as a value, and that would be the magnitude of the force. And something is wrong because I forgot to put an I here. So this should work theoretically. So if I'm doing this, shooting, you can see, oh, they're flying all over the place. And the reason they are flying all over the place is just because this force gets set and then it doesn't change. So they will just keep applying this force throughout, and we don't want that, so we need to have a way to scale it down. So we get this in the first frame, and then we just want it going down. Oh, sorry, I see I've done a mistake up here. Now this is not good. This should be primnum, so now actually it will probably look a bit different. No, not that different. Oh, anyway, what I'm gonna do is I'm gonna loop through this for each. I'm going to use it for each, and current trend, current force, and force agent. Okay. I'll take my force agent, and I'm going to set where it currently is in this. So I'm just going to set I. And I will of course count up each iteration starting on 0. So that way we will visit every position in that array. And then I'm going to do multiply equal, which means I'm going to multiply this by myself, and I'm going to do 0.1. In this way it will keep multiplying with 0.1, so it's going to get smaller and smaller until it's so small so you practically can't see the force. Cool. Let's see if this made a difference. So let's try this. Yeah, and as you can see, you get much more interesting hits. Instead of just falling down, they spin around, gets hit in the head, and so on. So what was I talking about matrices before? It's just because we're going to go in the intrinsics, and then we're going to extract all the transforms for the agents. And each transform will be a matrix. Start dropping down mockup biped 3. Going to hide this guy, and I'm going to drop down a geometry. And in here, I'm going to drop down an agent. And I'm going to point to this guy. So here's our agent. And now you just see the bones because I'm in wire mode, which is fine. So let's stay here. And now I'm going to drop down an attribute VOP. As you might remember from the first course, I was talking about that we have all these intrinsics that gives you a lot of power of what you can do with agents. One of the things we can do is to read and manipulate the rig for each agent. You can do this through either the agent local transforms or the agent world transforms. These are both arrays with a bunch of matrices that represent the position, orientation, and scale of each transform in the agent rig. So one way to get access to this is just to drop down an agent transform. There is also vex commands that do the same thing. And I'm going to take the prim num and the file name. I'm going to input 1 into the file name here, and the prim num into prim here. And then I'm going to, for space, I'm going to take world. So now, by doing that, I'm extracting this agent world transforms and put that into an array. So if I would do a bind export here, and just take a look at that, we have this array with matrices. So if I copy that, and I do a notepad, you have all these matrices here. That tells you the orientation and position of the different bones. That is cool. So let's see what can we do with this. So because it's an array, we can just loop through it. So if I'm using a for each, that will just loop through that array. I put the array in here, and I move this back a little bit. And just to prove that I get all this, I can use an extract transform. And this element out is the current iteration of the loop. So I'm going to connect that into this here. So by doing that, I can extract either the transform, rotation, scale, or shear. So let's take the transform and then add a point to each transform. By doing that, you see I have a point on each bone here. Perfect. Very cool. And if I would do an agent edit and say, let's take the left arm and rotate that a little bit, you see that the points are moving there because they are extracting the matrix. The thing that might be a bit confusing is that even if it's called world transform, it's not actually in global space, only in the world of the specific agent. And you can see this clearly if you put down a transform and rotate and transform the agent. The transforms aren't aware of where the agent is in the global space, only where they are in the agent space. So this means that we need to use another thing. So if we go into spreadsheet here again and look at intrinsics, we also have a packed full transform. And this packed full transform is a matrix that is expressing the position and rotation and scale of the agent. So if I would look at this guy here, now you see by default it's most ones and zeros, but if I would go and do the same thing here after I've oriented this guy, now suddenly you can see that this matrix has changed. So what we want to do is to parent the agent world transforms under the packed full transform. Luckily this is extremely easy to do with matrices. let's get this matrix here. Prim intrinsic. So now I'm saying I want the primitive intrinsics because it's in the intrinsics. And I'm going to take the first port here, and I'm going to take the prim to the prim here. So now we have that matrix. The only thing you need to do with matrices to parent them is to multiply them together. And by the way, you can parent a vector under a matrix by multiplying them together as well. The order is important though, and the parent need to be last. So if I do a multiply here, like so, this needs to go in first because it matters which one is first and which one is at the bottom. So the one that you want to be the parent will be at the bottom. If I connect this to this now, oh, you see that this line here is not full. That is just because by default the prim intrinsics is set to matrix 3. So that's why we just get the orientation here and not the position. But we want to have it as a matrix 4. As you remember, when you have a matrix 4, you also have the position. So let's put it like that. And also another thing I forgot to do. I didn't tell it. I just told the intrinsics to take the transform. But we want to have the packed full transform. Like so. So now we have, you can see that all these guys are updated, and just through the simple thing. Okay, let's try our transitions out. And just before we move on, I have created some more transitions. So before we only made the transitions for the one hand, but now I've done it for the two hand grip as well. And you can see that I've stacked two clip transition graphs together, and you can do that by plugging into this third port. The reason that I do this is just to keep it a bit cleaner, and it allows me to do one group of clips at a time. Especially if you have a lot of clips, it's a good practice to keep them separated. A thing to note though, if you want to do the same thing with the clip properties, you can't just stack them in a similar way, just because after the clip properties is done with the data, it's just sending out points, and the clip properties of course need to have the agents in to read the clips. So with clip properties you need to merge them together. Just a thing to remember. Okay, so let's go to the crowd sim. I'm just gonna turn on the terrain and let's go into the crowd sim. So the first thing we need to do if we're going to do transitions is that we need to tell them that there is a transition graph, and we do that through the crowd object. So you can hear, and then it's here when it says clip transition graph, you just point to it like so. Let's start doing an idle to a walk. We have the walk already. If you remember, I doubled the speed, so I'm going to take that down, and then I'm going to copy this and make an idle. So I'm going to call this idle, and then I'm going to merge it together like so, and then I'm going to change these guys to idle 1h and idle 2h. A cool thing with clips using a transition graph in Houdini is that it will make sure that in a state with multiple clips, only clips that are compatible with the current clip will be selected. So for instance, if the agent is playing the idle 1h that only has a transition to walk 1h, it will automatically pick that clip in the walk state. Oh, I'm gonna remove this little underscore here. So cool. Another thing I'm going to do, just to make it easier to see what's going on, I'm going to drop down a pop color. They are in the idle, they're going to be yellow. And then if they are in the walk, they're going to be blue. And you can see because walk was the default state, so it's starting with the walk. But I want them to start with an idle, so I'm going to go back to the crowd source. And I'm going to go in here and going to type idle instead. And let's go back to the crowd sim. Now you can see that they're all yellow and standing in this idle. So let's trigger these guys into a walk. And the way I'm going to do that is I'm going to drop down on geometry. I'm going to call this triggers. And then I'm going to create a sphere. I'm going to make that a polygon mesh. I'm going to make a transform. And let's show the crowd too. If we start over here somewhere, I'm going to keyframe this. And then around here, I'm just going to drag it through the whole thing. I'm going to keyframe that. So now it's just going through them. And what I want to do is, like, as soon as an agent is inside the sphere, it's going to get triggered into the walk. Let's call this walk trigger. And let's go in here. So to get this to work, we're going to need a trigger. So I'm going to drop down a crowd trigger. And I'm going to call this idle to walk. And then we need a transition that gets triggered by this trigger. And then we need a crowd transition. I'm going to plug this into that. And then plug it into the last port here. And the thing to note though is that if you use this in its default state, it's just going to do a blend between the clips. And then you can specify how the blend will be with this thing here. But for us, we have transitions. So we're going to check this use clip transition graph. And then of course we need to take the input, will be an idle, and the output would be a walk. And here in the trigger, by default, it is on object bounce, which is what we want. We want it to be triggered when it gets inside that sphere. And then I'm going to point to that sphere, out walk trigger. And you can see we get this template in here. For this, I'm going to choose continuous, so it keeps checking if they are inside or not. So let's try this out. So play. You see it goes over. They're turning into blue, so we know that they are in the walk state. Perfect. So far, so good. One thing we can see that the agents are clumping together. And the reason they are clumping together is because the force is too strong on the path. What I can do is I can go to this path variance and just loosen it up a little bit by allowing them to deviate a bit more. So I'm going to put this to 5, and then let's do that again. Now you can see it's much better. So far so good. So next thing we're going to do is to find a way to trigger them into a run state. Let's have a look at the crowd source, and I've deleted all these extra things from the previous video. So let's drop down a crowd source, and you can see that immediately I get something. And the reason for that is because it has this random distribution by default, so I can make more agents if I want to, or I can also relax their position, and I can also make it so it's a bigger area. But then a more interesting way to handling it is of course to plug something into the second port. So if I plug in a grid here, for instance, you can see that now it's going to scatter points on this grid. And it might be that in some cases you don't want it to scatter points on the grid because you just want to have it on points, and you can get that, but this crowd source, as soon as it gets primitives, is going to scatter along those primitives. But if you remove all the primitives by, for example, adding an add, like so, and then you have this option, delete geometry but keep the points. And if I do that and go back here, you can see that now I get one agent on every point. And other things I can do, because if we go down here, we have this density attribute, and that is if we are scattering. So say I'm going to delete that, and then I'm going to drop down a paint. So let's have a look at that, and then I'm going to apply background, and then I'm going to paint a little bit here, and a little bit here. And then I want to convert the CD to density, so I'm going to drop down and wrangle. And here I'm going to do float at density equals, and then I just want to take one channel. So in this case I'm going to take the red channel from the color. So if we go down to this now, we can see that they use the painted density to scatter the agents. Then you have, of course, the initial state, and this is a bit deceiving. You have this selector here, so if you click this, you can see that you get your clips there. But in our case, if we go into the crowd sim, our state is called jump. Even if it's pointed to long jumps, it's not called long jumps. So if I would put long jumps here and then see what we get from a crowd sim, we get these broken agents again, because then it doesn't know any state that's called long jumps. Yeah, it is a bit deceiving. So you have to type whatever your state is called in here. Oh, it's actually called jumps and not jumps. So jump. So now you can see that I'm back at that state. That is first thing. I'm gonna continue, and I'm actually gonna just delete this guy and just use the built-in scatter. So let's continue. Under here we have the scale, of course. So nothing weird about that. You have the initial velocity you're gonna have and a heading. If you have an initial velocity, it will overwrite the heading. The heading is if you don't have velocity, you can just tell it what direction it's supposed to be in. But you won't see it here in the crowd source. You won't see it until you're using the crowd sim. So now you can see they changed position. But as soon as if I would set in the velocity, it will go back and just override this heading. And then you have the up vector, which is of course what is up for the agent. And then you can also create groups by using this group thing. You have two tabs. So the next tab that is really useful is that you can randomize different things. So you can randomize if you have different agent primitives. Now we just have one agent primitive. We just have these legs. But if you would have different agent primitives, you could go in here and randomize them here. And here you can randomize the initial state. Now we just have one initial state, but let's create another one. So go into the crowd sim. I'm going to copy this actually. So now I'm going to call this long jump and this one short jump. And then let's merge them together. So now we have two states that goes into this state slot here. So we have long jumps, and for this one I'm going to select short jumps. So then we can go into the crowd source, randomize initial state, and I can have long jumps, and then I can do the next one. Oh, remove this walk. And short jumps. Oh, sorry. This is the same thing again, and I did it myself, because this is of course just Eclipse. So, and I didn't have an S in my state. So, long jump, short jump. And then you have a weighting if you want to have less of one of them or more of the other. So now we have different kind of clips. And then you have the randomizer clip times. You don't want them to start at the same time, which you usually don't. You can randomize the current layer. As you remember, we had two layers. So we have the costume 1, and then we can randomize, and some of them have costume 2. Now you can see that they are using different layers. And randomize scale, also kind of obvious. Same thing, initial velocity. You can all randomize that and randomize the heading and even the up vector. So yeah, that is a brief overview of the crowd source. So let's dive in more into the crowd sim itself. So now let us make a new transition. So what I want to do is from a walk to a run. So first of all we need to add a run as a state. And in this case I want the run to be basically the same thing as a walk. With that I mean I want them to avoid obstacle, I want them to follow the path. The only thing I wouldn't want is the color. So let's copy this, and then these two things I want, let's put a merge over these guys, because as you might recall, the only thing important is whatever is between these guys. So in this way they're sharing the same behavior. The only thing I didn't want was the colors. I want to have a separate color. So let's put that to red. I'll call this run. Gonna go up here, and then I'm gonna do that, run, and run. So the next thing we need to do, we need to have something that triggers them. So I'm gonna create a trigger. I'm gonna go into triggers here, and then I'm gonna drop down a curve. So what I want is as soon as they walk over this curve, I want them to be triggered to a run. I'm gonna paint the curve here. So perfect. I'm going to do a new out, and I'm going to call that run trigger. Out, run, trigger. And it's always black. Let's go back here, and I need a new crowd trigger. So I'm going to drop down a new crowd trigger. I call this walk to run. I need a new transition. And I need to merge these two guys together. So a merge, and then I'm going to plug it in there. So in here, of course, I need to walk, and then actually it's a walk to a run by default. So that's great. So just check this, use clip transition graph. And up here, I'm not going to use object bounds this time. I'm going to use object distance position. And here you can specify how close it is to an object. So let's go in here and take the run trigger. The default behavior is distant to centroid. We don't want that. We want the closest point. So closest point. And if it's less than 1, it gets triggered. So let's see what this gives us. Start walking. And you can see that guy got triggered to run, and that guy got triggered to run. Gonna fast forward a bit. And here you go. Gets triggered and run off. Awesome. One thing I'm gonna show you, just if you encounter it, I'm gonna create an error here. So you can see the transition are all working great, but it can be sometimes if you're changing the speed too much, they can get confused. So let's just try that. If I do the walk and the run speed up to 2, so it's like twice the speed, and then I'm gonna go to the end. Here is a perfect example. So you can see that some of them, by this everyone should be in a run, but not all of them are in a run, and some of them are actually standing still, but they are supposed to be in a walk state. What has happened is that they have been triggered to the walk to run intermediate clip, but because the speed is so high, if we go into the warrior setup, it gets triggered to this walk run idle, but then it just have one window to come out from walk run idle to run, and it just do that on 2 frames. And this clip is not looping, of course, because it's just a transition clip. So what happens is the frame rate is too high on the clip, so it misses these 2 frames, and then it never gets triggered. So in that case, if you are doing these extreme speed ups, you probably need to make this a bit higher. So if I would put this to, now my transition region is bigger, and if we look at this now, oh, I forgot, I need to of course do it for both clips, so I need to do it on this one too. So if I do this to 19080, and then do it again. Now you can see that all of them except this guy gets triggered. And this guy, I actually think that is because, yeah, he never gets triggered into that state at all. This is just a problem you get if you go with crazy clip speeds, but if you encounter this problem, you probably need to make bigger transition regions. So I bet I'm gonna go take this back to a normal speed. And I'm gonna also take them but yeah, so a lot of times the character you're gonna use in your crowd is rigged in another package than Houdini. So let's see how we can import that. So I have this character in Maya, this jumping leg here. It doesn't have to be Maya. The only thing you need is to have a package that can export to FBX, which basically all packages can. You see I have 3 pieces of geometry, I have this rig, and then I've exported this as an FBX. So let's go back to Houdini. So you can just drop down a geometry, go into the sub context, drop down an agent. Instead of input from scene, we're just going to go to the FBX option instead, and then point to one of these guys. And first, you get like this very tiny little leg. And the reason you get a tiny leg is because the default behavior is to convert to units, and it's assuming that the rig is too big. And a lot of times that is correct, but in this case I just want to have it 1-to-1, so I'm gonna uncheck this, and here is the leg in the right size. It's not a very good practice to always create the agents on the fly in every shot you are using them in. So I actually want to write them out, so then I can refer to the same rig from different scene files. So to do that you need to use an agent drop, and you need to go either into out, and you can drop down an agent drop here, or you can stay in object, but then you need to drop down a drop network. So I'm going to do that and call these bake agents. And we're going in here, I'm going to drop down an agent drop. And this is not the same thing as the agent swap, even if it looks like some of the options are similar, but this is solely for writing out the agents. And you could just go and select FBX and then do the same thing, select the short legs and then write that out. And that would be fine. But I don't want to do that in this case, because as you saw I had these 2 variations. So I want to create 2 layers with these variations and then write them out together with the rig. If I would just point to the FBX, I don't really have any control over how my layers would be. I just get a default layer and a crude collision layer. So then I can use the other option here, which is just writing out from an agent primitive. So I can just point to this agent primitive and write that out. Now this doesn't make any sense, because this is basically as I would just point to the FBX, because I haven't done anything with it. But let's go to this now and then drop down an agent layer. So here's an agent layer, and I'm gonna call this costume 1, and starts empty. You can base it on another layer if you want to, so I can base it on default, but I don't want to. And for the layer name I'm gonna use the built-in variable $OS. So what this does is just take the name from the node and then it sets that as a layer name. So it sets it to costume 1. So then I'm going to go down here to layer bindings. For transform names it doesn't really matter, because the geometry is driven by the rig anyway. But I'm going to choose world root, and then I'm going to choose the leg variation 1. So here you can see that one. And then I'm going to add one more also word root, and I'm going to select the bolt. So here's my first variation, and then I'm going to copy this node, and I'm going to put this after this one. And as you see, it just renamed it to costume 2, and because it's $OS, this will also be costume 2. And the only thing I need to do here is to change this shape, the robot leg version 1 to robot leg version 2. So perfect. So now I have these 2 layers. So let's drop down now a null here. I'm going to call this out agent prim. I'm going to color it black to show it's out one. And then let's go back to the agent drop. So here, instead of pointing to the agent sub, I'm just going to point to this out agent prim. Great. And then for the rest of the agent name, I want that to be leg. And for the cache directory, I'm just going to leave all this as is. And then let's write this out, save to disk. And if we look now, you can see we have this new agent folders created. We have this leg, and in here we have the 2 costume 1 layer and costume 2 layer. And if we would look at these in a text editor, we can see that it's deforming geometry. We can see what shapes are showing. So yeah, perfect. So to read this back, let's call this agent prim, and then we're just gonna make a new one here. Call this agents, and I'm gonna drop down an agent sub again. And I can use, instead of scene, I'm just gonna take disk, because I want to have the saved out reference. And because I didn't change these guys, this will point to the same folder. I just need to rename, because this is really important, because it doesn't know what it's looking for. So you have to have the right name here. So I'm gonna write leg here, and here's my agent, and with my layers. So I have costume 1 and I have costume 2. Oh, I'm gonna unhide that. Costume 1 and costume 2. Perfect. So now we have our crowd agent. Okay, let's have a closer look at the hard constraint. And to do that, I'm going to drop down a geometry. I'm going to delete this, and I'm going to drop down a sphere. And I'm going to make this a polygon. And put this to 3, put down a transform, so I can move it up a little bit. Something like this. I'm going to use a Voronoi to fracture it. Like so. And I'm going to drop down a scatter. So I have some fracture points here, and I'm going to put this to 30. And I'm going to visualize the pieces so you can see them. So here are the pieces. Cool. So the next thing we need to do is to make this to packed primitives. I'm going to use assemble. And in here you have this create packed geometry. So in this way, now every piece is a packed primitive. Now we need some polylines for the constraints, so I'll use connect adjacent pieces that will create polylines between the different pieces. And here I'm going to use connection type adjacent pieces from points. Perfect. You don't see anything though, it's just because the search radius is too small. So let's get up that a little bit, 3 as max connections. So here we have some polylines that connects our pieces. And before, the 2 points on each polyline was the same place, so the rest length was 0. But in this case I want to use the actual length, so I'm going to set this, and then it's going to save the actual length as a rest length. Cool. Okay, so let's drop down a DOP network. So the DOP network is here. I'm gonna connect these guys in here. We're gonna have a rigid body solver. Put in here. We need a packed primitive. So everybody packed object, and in here let's take the geometry source, point to the first context geometry, and the first context geometry is this one guy here. So in this way, now we have this guy in here. And what do we else need? We need some gravity so it can't fall. We also need it to collide with something, so I'm gonna drop down a ground plane. So the ground plane is here, and then I'm gonna drop down a merge, and here is the merge, and in with the ground plane, and I want it to the left because left inputs affects the right inputs. So now we have a simulation at least, but it's just breaking apart, not really what we want, and so we need to create the constraints as well. So let's drop down a constraint network. Here, oops. Here is that, and in here, geometry source, let's do the second context geometry, which is this one here, where the different polylines comes in. So the next thing we need to do is we need our hard constraint. So let's do a hard constraint, connect it in here, and let's name it pin as before. But currently our polylines doesn't have any constraint name because we haven't specified that yet. So now it doesn't know what to look for, so if we would play this, it will still doesn't work, and we could get this error because there are no constraints. So let's go and define these names. So we're going to drop down a wrangle here, and we also make sure we want the name on the primitive and not on the point. So let's change this to primitive, do s as in string, attribute s at constraint name, and we want this to be pin. Alright, so this should work. If we go back here now and try it, perfect. We can see that this sphere is holding together by the constraints. So the first thing we can see that there are two constraint types with hard constraints. So if I'm gonna put some velocity on this, and then you can see the default constraint type is just the positions. So it doesn't try to constrain it by the rotation. So if I put this to -20, and boom, you will see it a bit wonky because it's only constraining the position, not the rotation. If I would change this, you can just specify that the constraint type as rotation, but I want both positions and rotation, so I'm gonna do another attribute here as constraint type, and I want this to be all. So now if we do the same thing, it's a little bit better. Cool. Let's continue. What else can we do here? If we said, I'm gonna set this more to -10, so it's not as crazy. If we look at the hard constraint, we have these two things. We have the rest length. So the rest length here is 1. Before it was 0 because the anchor point was at the same position. But in this case it isn't, and we have set the rest length in an attribute. That value will be multiplied with this value. We also have the constraint force mixing and the error reduction parameter. And the error reduction parameter is how much, if constraint gets violated, is how fast it will try to correct that error. So if we would put this to 0, it do no correction. So then it will just sliding apart because it doesn't try to correct it. If we do it really extreme, put it to 1, and now it tries to do all corrections on the same frame, which results in a lot of crazy forces and makes it very unstable. So the recommended values are between 0.2 and 0.8. So let's put 0.2 again. And constraint force mixing it tells that the constraints can be violated if the force is strong enough. So if I would put this to 1, now it's allowed, the force was enough to get them violated. And even if I would put this error reduction to 1, it will still get violated just because of this constraint force mixing. Moving on, let's drop down a mocap biped 3, and I'm going to take the T-pose. I'm going to hide this. I'm going to drop down a geometry, delete this, and drop down an agent. And I'm just going to read the mocap biped 3 by going here, mocap biped 3, I have an agent, and then I'm going to rename this clip to T-pose. Alright, okay, so I want to create two collision objects here, so I'm going to drop down a collision layer, and I'm going to create one here, drag it out a little bit, up, and then I'm going to create one for the arm. So now I have these two collision objects, and I'm going to create a constraint. Or actually, I'm just going to define the limits of that constraint, because the constraints is going to be created later. Before, we just used this to create the hard constraints, but now we're going to use the cone twist constraints, which are the most common ones in ragdolls. I just have this little dot here, this is selected. Either I can just click plus and then select it, or I can just click here, and here are my limits. And currently they are very strict, so you can't move at all. And I have this twist value and an up rotation and out rotation. So let's see what these do. So if I start with the out rotation or the up rotation, now it's more obvious what the limits for these constraints are. I have the handle, and obviously the arm will be able to move within this. And right now it's just on one axis, so it's not much of a cone. But let's start with this. Now I just want to test this, so I'm going to drop down a test simulation ragdoll. But one thing we're going to notice immediately if we start using this, I just want the arm to be animated and the rest of the guy to be static. But obviously he's just going to fall down. It's going to look really weird because we just have a collision object for his chest and his arm. And yeah, not at all what I wanted. So what I want, I just want to have like a partial ragdoll, just this part. And after 16.5 you can specify all the only parts of the agents are ragdoll. To use this we need to drop down an agent transform group. And if I go in here, so I want it from the shoulder and to the arm. I have this group name, let's call this arm. And then I need to take the root, and then so I'm gonna select this shoulder. So if I go to left shoulder, let's see here, left shoulder, boom. And if I check this show guide geometry, see I get these little spheres here. And these spheres indicate what parts of the rig that are included in the transform group. Let's see if this works. But it won't work just like this. We need to tell the simulation to use it. If I just play it now, it's just going to be like before. But what I can do is that I can allow editing of contents here. So I can go in and find the actual DOPSIM. And then I can go to the state, the ragdoll state. And here you have this little checkbox, partial ragdolls. So I'm going to do that. And then I'm going to select the group here. You get an active group. So I'm going to select the arm group. And everything seems a little bit broken. And the reason for that is it knows that this part here is going to be ragdoll, but it doesn't know what the rest of the part is supposed to be. What you need to do is you need to tell it that this part here will be ragdoll, but this part here will just play a clip instead. So I'm going to select this clip here. You have this clip name. I'm going to select the T-pose, and ta-da! If we go back here and look how this looks, and now we can see the arm is just falling down. And also if we look, you can see that it stops within this guide. Cool. And yeah, and obviously if I do it longer, it will fall down here. Cool. And of course we can use the other axis. So if we zero this out and make this minus 30 and 30, we have it in this axis instead. And obviously if I play it now, it won't fall down because it's not allowed to go down anymore. I can go into gravity, and instead of having a value in Y, I can change the axis to Z. And then you will see it's following that guide instead. If I turn the other range back on, you can now see that they form this little cone that constrains the joint. The final part of the cone twist constraint is the twist part, and you can turn that up by changing the twist rotation range. So let's set this to minus 10 to 10. You can now look at these yellow lines to see what the limits are for the twist. And a really important thing is that this orange up vector needs to be between these twist constraints. Otherwise, the whole arm is just going to be snap in a really weird position. Another thing that you can use this test simulation ragdoll for is to see if you have any weird constraints. Say that this limit would be in the wrong place, and if you remove the gravity and the initial velocity is zeroed out, that means that the only thing that can affect the limits are the constraints themselves. That means that if anything moves, the constraints are wrong. So in this case, you see the arm would move down just because it's just tried to follow the boundaries. You can see that the arm doesn't snap to its limits, but instead gradually gets there. And that is just because a new feature in 16.5, if this loud initial violation of limits isn't checked, then it will just pop into place. And so you see, like on the first frame, it's just snapped there immediately. And if it would say that you would have a clip, it would transition from a ragdoll. It would just be like a really unnatural snap. Before, you always had to make the limits fairly wide to avoid getting snaps when you triggered from your animation clips. And these wide ranges tended to give you very floppy arms, for example. So yeah, that is a little bit of cone twist constraints. So let's finish this guy up. So just one more thing to do, and that is to add sparks when they get hit. So to do that, I'm going to drop down a geometry. I'm going to call this sparks. And the thing is, we have all the data that we want and need for this from the agents. So I'm going to drop down an object merge. And here I'm going to point to the agents. So like here, out agents. And then I'm immediately going to delete them. I just need attributes. So I'm going to do an add. And here delete geometry but keep the points. And like so. And then I'm going to drop down an attribute delete. And I'm going to delete everything except hit, because I want to know when the agents are hit. I'm also going to keep the hit position, because I want to know where they're getting hit. And last of all, I'm going to have the hit direction. That was the direction of the raycast, and that we want them to like spray out from the agent. So we have all this, and we can see if I do a spreadsheet that I have only that now. Well, I have some groups too. And then I can drop down a blast, and here I'm just interested in these points when they are getting hit. So if they're not getting hit, I don't want them. So I'm going to set an attribute, and if hit is equal to 0, then I'm just going to blast it and put this point. And now we can see if I go, and I'm going to put on points here so we can see it better. You just get it when they get hit. But the point is at the wrong position, but that's an easy fix. So let's drop down a wrangle, and in this wrangle we are going to set the point position. So P equals to the hit position, which we know is in the right place. So by doing that, you can see suddenly the position is at the right place. We also need a velocity. V equals to the hit direction, and that is everything that we need before we start the actual simulation. So let's drop down a DOP network. I'm going to connect that into here, and in here I'm going to drop down a pop solver. I'm going to drop down a pop source. I'm going to drop down a pop object. I'm going to drop down a gravity and a ground plane. And what else do I need? A merge. So let's connect all these together. So I'm going to connect the pop solver. I'm going to connect the pop object and the pop source and the gravity and the merge here and the ground plane. And then I am going to change the order here. And here for the pop source, I am going to do points use first context geometry, which is this one here, of course. And by having that, we should have something already. I'm going to turn off the points here. And we can see now we have points that are bouncing away. Not really what we want. So let's first of all turn off that bounce here. So 0 and 0. And then here I want to have a just born group that we're going to use in a minute. And I'm also going to set this attribute, use inherited velocity. I'm going to set this to add to inherited velocity. And I'm also going to scale the velocity to 4. And then I'm going to have this variance here. So by having that, we have something more interesting. So actually that looks pretty good already. But you will notice one thing that will be a problem with this. That is that it sprays away too far from the agents. So what I'm going to do now is I'm going to scale the velocity a little bit. So some of them can go this far, but I want some of the points to be closer to the agent. I also want to add some extra randomness to it. And I'm going to do that by dropping down a subsolver. So here is a subsolver. And then I'm going to drop down a wrangle. And here in group, I'm going to use this just born group. It's called born. All the particles are in that group just when they get born. And then they are not in that group anymore. So then I can have this wrangle just to do its thing on the first frame when they are born. And then it's not going to happen again. So in that way, I can do the velocity. And I'm going to multiply it by itself. I'm going to have a random at ptnum, and this function goes between 0 and 1, so some of them won't have a velocity and some of them will have the old velocity. And then the last thing, I'm going to add the randomness I was talking about. So I'm going to do an attribute randomize, and then I'm going to do this rand orient. It's going to be a vector. I'm going to do this inside sphere. I'm going to have a cone angle of 30, and then I'm just going to multiply that here too. So I am going to do this vector and this rand, what did I call it? Rand orient? Rand orient, yes, this rand orient. And like so. So if we look at that now, go up here, hide, I'm not going to hide it, I'm going to show all. And I'm also going to drop down a .io and just point to the .net and the pop object, and then I'm just going to have a field here. So like so. So if we look at this, we can now see that they are getting hit. Alright, so let's get started. So in this scene I have created a little snowman. So I have him in a rest position here, which means that he's not moving at all. And then I have him doing this little wobble. And I also have this terrain, which is just a grid with some noise applied. So the first thing we need to do is to get this snowman to be an agent. So let's drop down a geometry. Call this agent setup. And in here, I'm going to drop down an agent sub. And as you might recall from the previous course, you can just use this and point to subnet. So I can just point to the snowman rest here. And then suddenly I have this snowman in a rest pose. And I'm going to call this rest here. One problem though is that with this method I can only get one of the clips, either the rest pose or the wobble. And if I would try to add a clip to the agent by dropping down an agent clip, you can see that the only option I have here is either from chop or from file. So one way to get around this is doing this little trick. So I'm gonna take this, I'm gonna copy him, call this wobble, then I'm gonna point that to the wobble animation. So here is my wobble animation, but now I have two separate agent primitives. And I just want to have them combined as one agent with two clips. But what I can do is I can create a chop network. I can go in here, drop down an agent. I can point to this wobble and select the wobble. So now if I look in here in the motion FX view, then you can see that I get all the animation curves. So what you can do then is just go back to agent clip, use this chop, go into the chop and select the agent here, and then call this wobble. So what I'm doing is to extract animation curves from one of the agents through chops, and then create a clip for the other agent by pointing to that chop network. You can see I have the rest and the wobble. Perfect. So let's put down and null, and call this out agent. I'm gonna call this black. Great. Alright, so now it's that done. So let's create the crowd. I'm gonna turn on the terrain here, and I want the crowd to be only in this little valley. So I can go into a drop down another geometry, call this crowd layout. If I go in here, I can do an object merge and point to the terrain. And I'm gonna do another object merge, so I'm gonna call this terrain here. And then I'm gonna have the agent. And then I'm gonna point to this agent setup and out agent. Actually gonna move it like this instead. Right, cool. First I'm gonna select the terrain, I'm gonna drop down a paint. Go to background, apply black to all. Just also gonna hide so I don't see the terrain from outside. And then I'm gonna make sure that this tool is selected, and then I'm gonna just paint into here. Like so. I'm gonna drop down a scatter now. All of this is of course things that you have seen before, so I'm just gonna lay down everything really quickly here. For the density, I'm gonna use CD, so now I have that. I don't want the color, attribute delete. And then I run CD here. I need a crowd source. This crowd source is gonna take the agent, and it's gonna take the points I just created, like so. And here are all my agents, maybe less agents, like 200. And let's go to the crowd source and go to randomize and randomize the clip time. Out crowd. One thing I forgot to do is I also want to create some loop properties. So if we turn this off first and look at the snowman, turn this off. This animation has a loop range that basically is around 87, so 1 to 87. If we go back to agent setup and then gonna drop down an agent clip property, and then we can select the wobble, loop range 1 to 87. Then I'm gonna make an out properties, like so. And the last step to have a working crowd is to drop down a DOP network. So let's have a DOP network. I'm gonna call this crowd sim. Go in here, crowd solver, and a crowd object, and a crowd source. Oh, and a crowd state too. First connect this, the crowd object in here, the crowd source in the second, and the state to the third. State I'm going to call wobble. Let's first go to crowd source and select the crowd and go to the first frame. So here's the crowd, and here is the wobble. I can select the wobble clip It actually would, because now we're saying $OS, it would still pick up the wobble clip, but just to make sure I selected it here instead. And in the crowd object, I can go to clip properties and then point to the clip properties here. So out properties, and if we don't want them to move like this, let's go put this to locomotive. Actually, then they're not going to move. It's going to be in their little position here. Perfect. Alright, let's finish up by setting the initial state, and in some versions of Houdini it will break the agent if it's not set. So if we look at it, we have our terrain, and we have a lot of wobbly snowmans. So in the next lesson, let's build some collision shapes for these guys. So we have the simulation, but as you can see, as soon as these guys goes into ragdoll, they're just falling apart. And of course, most of the time when you're working with ragdolls, you don't want that. You want the different limbs to stick together. So let's take a look how we can do that. The first thing we do is go into the agent setup, and I'm gonna drop down an agent configure joints. And in here you can define different joint limits, but I'm not even gonna do that for this example. Just by adding this, we get these attributes added. And you can see if I turn that off, we don't have them, and then I turn them off. So we get these attribute arrays. And these are useful for the next node we're going to drop down here in the crowd layout, and that is the agent constraint network. And the first port is just piping out the agents, and in the second port it creates the constraints. So if we visualize the second port, you can see we don't have the agents because it's just a constraint. But let's see what the constraints are then. First, at the point position, we have the anchor points. And so every anchor point, they defined what is sticking together. So here is the point position, and we can see if I visualize this, we can see we have all these points here. So here we have the point position, and at the end here, for the name, we have the agent, which is agent 0, so that is agent number 0, and then it's defining what body part this anchor point is for. So in this case it's the hat, and here is agent 0's head. We can see that these points have the same point position. So if we go and just take a look at that, so if I move one of these points, you can see that it's actually a line. It's just that both the anchor points are at the same position, so you don't see that it is a line, but it is actually a line. So let's go further. So we have this first anchor point, which is the hat, and the head is connected. So here in the vertices we can see that primitive 0 have two vertices, 0, 0, 0, 1, and 0, 0 is point number 0, which is this one, and 0, 1 is point number 1, which is this one. And if you go to the next one, you can see for primitive 1, the vertex 0 is 2, which would be this one, and primitive 1 is 3, which would be this one. Alright, so that defines what points each polyline is made up from. So let's go to the primitives then. So let's look at primitive 0. And here we can see we have like all these attributes. And in our case, because we are not using the joint constraints, a lot of these attributes doesn't make any sense right now. So most of these attributes are defining the joint limits. But in our case, we're going to use this built-in. If we look at the agent constraint network, we have this checked, pin shapes with no rotational limits. So what this says, if we haven't defined any rotational limits, then this is going to make a hard constraint. This calls this pin, but it's going to set up a hard constraint. If you use the crowd tools and setting up a ragdoll network, this would be a hard constraint. the most important thing for us here is the constraint name, which is pin. We need to remember that. And the constraint type is all, which means that it affects both the position and the rotation. What the hard constraint has to do is try to make sure that these two are sticking together, but you can actually, if you apply a lot of force to it, make it overextend. But we can talk more about that later. For now, we just can see that all of these guys are going to be hard constraints. So the next thing we need to do, let's remove this guy, is to go into the DOP sim here, and then we're going to set up a hard constraint. So first of all, I'm going to drop down the constraint network. This is telling our crowd simulation that we have constraints for the different agents. And now it's erroring out because we need to give it a couple of things. First of all, we need to give it a constraint. So let's do a hard constraint. Do a hard constraint relationship. Gotta plug that into here. Here for the rest length on the hard constraint, as you might remember, the two anchor points have the same position, which means that they have a rest length of 0. So we're going to set this to 0. And let's also point to the constraint network. So let's go into here and go to crowd layout and out constraints. So one thing we need to do, because remember when we looked in here in the spreadsheet, we have this constraint name. So we need to tell this hard constraint that that is the name it should use. If we take data name and put this to pin, now it knows that every primitive with that attribute is a hard constraint. So if we look at this now, we can uncheck this display geometry, and here we can see that it has applied 3 hard constraints on each agent. And you can see it's not on every point here. It's just going to put a constraint between every collision geometry. So it's going to be one between these guys and one between these guys, and then one for the hat. So let's go back here. So here you can see that they are constrained together. And let's go back and just turn that back on again. If we play this now, you can see that all these snowmen are holding up together. So now they're just acting like some small stiff units. Cool. Just to break it up a little bit, we can say like, oh, we don't want all of them to be a unit. We want some of the pieces to break apart and some of them to stick together. So let's do it in a very quick and easy way. If we go to crowd layout, and I'm going to drop down randomize attribute. We'll call this break. It's a primitive attribute. We're going to have it in one dimension. We're just going to have it as a float, and it's between 0 and 1. So if we look at this now and take a spreadsheet, we can see that the break goes between 0 and 1. And now when I have this, I'm going to drop down and blast, and then I'm going to say this break is greater than 0.5, which means for half of the objects, then delete that primitive. So if I do primitives, look at that, you can see now it deletes half of them. What that means, you have all these primitives that defines that it's a hard constraint, and we'll delete half of them. So some of them won't exist anymore, which of course means that some of them are going to break apart now. So if we play this, you can see here the hat is falling off. These pieces are still together. All these three are together. So now it's completely random what part is holding together or what's breaking apart. Okay, back to this again. And now we're going to put all that newfound knowledge to good use. Right now, all the agents are dropping straight down when they're triggered, and I want to apply some force right at the position where they get hit. The first step to do this is to get the actual hit position, and then see what agent transform is closest to that position. And I'm back here in this attribute up here. If you remember, it was looping through the different bullets, and then it was raycasting backwards to see if it hit the agent, and if it did, it set hit to 1. But we will need some more things now. The first thing we need to save out is the position where the agent gets hit, and we can get that from the intersect node here. The second thing we need is the direction of the bullet, so we can apply the force to the agent in the same direction. And for this, we can get the shot deer we use for the intersect ray direction and inverse that. I could do what I did with this two-way switch, and do that 2 more times, but I'm actually going to use an if block now instead. So an if block works like this. The condition is true, it's going to do whatever is going on in here. A very easy concept. Let's see if it's hit. So this compare here is a test to see if the agents get hit or not. If the agent is hit, I want to save out the position. So in the first port here, and I also want to have the shot there. Let's do that in here, and then I'm going to drop down to bind exports. First I'm going to do a hit position. I'm going to call it hit pos in there, and I'm going to copy this guy, and I'm going to use this for the hit direction. Hit there. Right. I got an error here, but I just middle clicked the node to make it go away. Another way to get rid of these false errors when they are more persistent is to do a Control X and then just do a Control Z. But anyway, now this should be working, so let's go out and do a spreadsheet. Oh, like this. And let's see if they get hit. You can see that guy get hit. And by the way, here's also the reason why I kept this as it was, because I want this hit value to just be one on the frame where he gets hits, and then I want it to be zeroed out, so it does that. But when I do it this method, you can see that he just sets the values, and then it's going to be these values until another value is set. Yeah, you can see that they stay the same. Okay, we have the hit position, and now it's time to get the position of all the limbs for each agent. And this one, I just want to run it on points where the hit is 1. So only on the frame when the hit value is 1. So I'm going to do at hit equals to 1. And I'm going to run this over points. So like so, and I'm going to call this check rig. Let's go in here. And as you remember, we need to get the transform from the agents. So let's drop down an agent transforms. And I connect this in here, and this to the prim number. So, and I also want this space to be world, and then I need to loop through this, because now this is just brought into an array. So let's do a for each here, so we can go through the array, and then connect this into this, so like so. And now for every iteration, is this element out will be the matrix for that transformation. As you also remember, this didn't take in the scale and the position and orientation of the agent, so we need to multiply that in so to get it to work. So let's drop down a prim intrinsic and connect that in here, and here prim number, and here I'm gonna write pack full transform, and this also needs to be a matrix 4, and I'm gonna drop down and multiply like so, and then I want to extract the position from this, so I'm going to drop down extract, like so, and let us just see so this works. So I'm going to drop down an add, or an add point rather, and I'm going to connect that into here, and let's see. Actually, it doesn't work. So, it doesn't work because no one is hit on this frame. So let's go to see someone is getting hit. There, that guy gets hit. And then you can see all the points are in the right places. So let's delete that guy. Cool. So now we have this. So what we need to do now is we need to take in the hit position. So I'm going to do a bind, and then I'm going to do a hit pos, and I'm going to use the vector. And I want to check the distance for these guys. So cool. Now we have a distance. And what we're going to do is we're going to loop through, and we want the one that has the shortest distance to the hit position. So let's do that. So let's first drop down a constant here, and I'm gonna plug that into this here, because this is the value I'm gonna compare to, because it's gonna iterate over and over again, and then this will always have what currently is the shortest distance. If we compare these two guys, so if this new distance is less than the old distance, then we want to save it. This is not enough though, because on the first iteration, before any distance has been saved, the old distance will be 0, and there will obviously never be a shorter distance than 0. So let's drop down an OR. Either this is true, or this other thing is true. What we're going to do there, we're going to check if this is 0, that means that this is the first iteration, and then we also want to save this value. Cool. We can do this two ways, but I'm going to use the if block for this. So let's do the if block. I'm going to connect this in here, and I'm going to take this value, I'm going to plug that in here, because what this means is if this is false, the value will go unchanged through the if block, but if it's true, whatever happens in the if block will come out. So if it's true, then I want to have the actual distance, like so, and then I'll connect that at the end of the for each block, because as you remember, this will make the for each remember the value in the next iteration. So now we have a working loop. The other thing we want to have is that we want to take the current index here. If we know the position in the array, we know what limb we're going to use. So let's take and just plug that into the second one there, and then I'm going to drop down a bind export, and it's going to be an integer, and I'm going to call this rig ID. This rig ID will now store the array position of the transform that is closest to the hit position. Cool, we're almost there. So now we just need to apply some force to this. But let's do that in the next lesson. So we have our collision shapes, and now it's time to set up the constraints for the joints. And I'm going to drop down an agent configure joints. This used to be really tricky, because before we had, I'm actually going to drop down a test ragdoll sim here, just to show what I mean. And before we had this allow initial violation of limits, it was really easy to get a natural snaps when triggering ragdolls, but now it's much less of a problem. Just so you know where this is actually in the sim, it's on the constraints. If I would go into this test ragdoll sim, you can see that it's actually on this cone twist constraint, and there is allow initial violation of limits, just so you can find it yourself. Okay, so let's put that inside. Let's start with the head. For the head, I usually don't want it to be able to arc back too much, and actually in general, you don't want to give your joints their actual full range of motion, because then you'll just end up with very floppy limbs. Try to have them constrained to some kind of mid-range. So in this case, I will do, that was a little bit too much, maybe something like that. And then usually I stay away from this twist rotation range. For heads, you can actually have it. So if I press Z, which is a shortcut to get the handle for the twist, so I'm gonna get that out a little bit. So if I switch back with F to rotation angles, now you can see these yellow guys, and it is really important, as I said before, to have this up vector here in between those. Otherwise it will try to snap back there. Okay, so here's the head, and then let's move on to the shoulder. And for the shoulder, there's also a tricky area. Your shoulder actually have a lot of flexibility, but if you give it the real range of motion, you're gonna get very floppy arms. Depending on what kind of shot you are working on, give it something that works for that shot. I want to have the arm be able to go down, so I'm gonna have that kind of generous, and maybe go forward, not that much backward actually, so more something like that. And in some cases I guess it could go more upwards, but I'm gonna take it down a little bit, so it would be something like this. And I'm staying away from this twist rotation range here. I know that Side Effects has it in their setup, but I want to get problems from it. So, and then I'm gonna go to the elbow, and here I just want to have the rotation on one plane. Let's see if I can move this silly thing. Okay, so let's here we go. And for this you can see it's not entirely where you expect it to be, because you want to, if you look at his elbow here, you don't want it to go up that plane. That is like a weird way of rotating your elbow. So in that case I will press O, and then I will rotate this cone in place. And by the way, you can get all this handled by right click, and then you will have the handles there. And so O, rotating it. This is more something I would expect. Pressing F again, so I can continue working on it like this. And now you can see that this twist range and this up vector is not aligning anymore. But that doesn't matter just because we have 0 in the twist rotation range. So then you don't have to care about it. Otherwise it would be a problem. And for the hand, I just want to have a little bit of up and down. Something like this. And here is also a place where I obviously need to rotate it, so press O again. I'm gonna get it something like that. And maybe rotate it like this. Something like that. I don't want to have that much motion. I just want to have to feel some flexibility, but I don't want to have all the hands to be in a 90 degrees angle either. Something like that. When I can get away with it, I try to keep the rotations in one plane, because there's nothing worse than a wobbly body part. Let's go to the spine, and I'm just gonna put it a little bit back. If I push it a lot back here, you're gonna get a lot of arcing, so I don't want that, so I'm gonna keep it like this. And then I'm gonna do a tiny bit just to get the feel that has some flexibility. Once again, I'm staying away from the twist rotation range. Going down here to the legs, the rotation will be quite off. And I'm going to press O and just align this with the bone here. Here I'm also staying away from the twist rotation range. But say that you would want to have a twist rotation range and then they are not aligning. To fix that, you press Shift O, and then you get this child rotation. So then I can rotate that to align. But in this case it doesn't matter, but just so you know. So we have it something like that, and now I can fix this. Maybe go up, so you can move boom. I will do the knees. Knees are very straightforward, just one axis, and I would have it something like this. And then for the foot, also kind of straightforward. I usually, most of the time, I don't want it to be that much. Something like that maybe. Here is an example of an artistic choice with your constraint limits. If you make the knee range very wide and allows the feet to bend up, you'll get agents that tend to drop straight down on their knees a lot more, while in this case, when we have a more moderate range, the agent will just fall over. So do a lot of experimentation and see what kind of look your setup will generate. Before we are moving on, let us just see how Side Effects preset looks. So I'm going to drop down another agent configure joint. Agent configure joints. Let's go here. And let's see that here. I have to say, I think you get pretty good result with this setup, but there are a lot of things that I wouldn't do in it. Like I said, I want to have the knees on just one plane. They have a lot of twist rotation in their setup, which I usually find troublesome. And one thing that I found interesting is that you can see here on the shoulder, you have the rotation up is not actually between the rotation guides. So if I would drop down a test simulation ragdoll and connect this guy here, You will see this very clearly if I go to constraints and turn off this allow initial violation of limits and look at his arms. Boom. So that is actually a very good example, and see why you need to have this between in the limits, otherwise you're gonna get this kind of pops. But like I said, a lot of times it's actually worked pretty well. So now we have our collision layer and we have our joint configuration. So cool, let's do a simulation of this. The first thing I'm going to do now is I'm going to drop down a crowd source. And actually I'm going to do another thing too. I'm going to change this mockup by 3 that is just a T-pose, and I'm going to change that into a zombie. So I'm going to use this zombie walk instead. Cool. And to update that, I'm going to go into the agent. I'm going to call this walk now. And I'm going to do a reload. Okay, right. Let's go to this crowd source. So now we have all these guys here. I'm going to put this to hide. I want a bigger area, so I'm going to put this area to 15. I also want the animation to be offsetted, so I'm going to randomize clip times and put it to 5 maybe. So here they are offsetted. Cool. So let's drop down a DOP network. And actually before, we can't forget the agent constraint network. So in this way, it will pick up all the configuration we have done here and create constraints from this. Let's put that into the first port here, and then I'm actually gonna drop down a null here in between. I'm gonna call this constraints. And I'm gonna put that into the second port here. Alright, let's create the simulation. So first we need a crowd solver, because I want them to walk and then I want them to be triggered into ragdoll. But now we're going to need two things, because we have the crowd solvers when we're using the clips, but then we want to use the bullet solver. So we have two solvers that we need to combine here. But drop down the bullet solver here too. And as I hope you remember, you can do this very thing with a multi-solver. And I'm going to connect the crowd solver first and then the bullet solver. I'm going to drop down the crowd objects. Here's where the crowd is living, and usually I put it in the first port of the crowd solver, but now I want both the crowd solver and the bullet solver to be able to use it, so I need to put it here in the multi-solver. So in there, and then I need a crowd source. I have the crowd source here. I'm going to put that as usual in the second port here, and here in geometry source I'm going to use the first context geometry. So the first context geometry is of course this one that comes out here, and then let's go down here, and now all of them are broken. It's just because we don't have a state yet. So that's the next thing. Let's do a state here. A crowd state. And I'm going to start with a ragdoll. I'm going to make this active here. And I'm also going to go out here at the initial state. I'm going to type ragdoll. So here are our guys. Play this, nothing will happen. They will just stand there, frozen. And the reason for that is that we need a couple of things. First, we're going to need gravity. They haven't any constraints yet. They're just going to fall apart if we're going to put gravity here. We need something to collide on. So let's start with the ground plane. And we're going to merge this in here. So merge. And to the left, because left inputs affects the right input. And we need the gravity. And then, of course, we need the constraint network. So let's drop down a constraint network. And this time we have two potential constraints. Before we only had a hard constraint that we called pin, but this time we also have the cone twist constraint. Or actually, as we are using the preset, we won't have a hard constraint, but I'll put it there just in case. So I'm going to do a merge here, and I'm going to have a hard constraint. I'm going to put it in here, and like before, I need to put this into pin, and I'm going to set the rest length to 0. And the next thing I need to do is to have the cone twist constraint. So that goes in here. And let's see what is the name of the cone twist. If we go in here, we can see our name. So we can see the constraint name is cone twist. And like before, if I would uncheck one of these guys, because now all of them are cone twist constraints, but because we have this pin shapes with no rotation limits, so that means as soon as I don't have a cone twist constraint anywhere, like if I take that away, that will create a pin constraint, which is a hard constraint. Let's get that back in there. So it's called cone twist. Let's go in here again and call this cone twist. And all these top values here, max up rotation and max out rotation, and max twist and softness, all of these guys are going to be multiplied by the constraints you set up before. So let's set this to 1. In this way, you're going to get whatever you set the values to in the agent configure joint node, because it will be multiplied by 1. Otherwise, you will have to go back and forth, and it would be much harder to get an overview of what the actual constraint values are. So put all these guys to 1, and here all these guys are the guys that we can find on the agent constraint network. These guys, and the same things goes here. So they're going to be multiplied with those values. So put all of these guys to 1. Cool. All right. And the last thing we need to do, we also need to tell them where to pick up the constraint network. And in this case, it's in the second port here. So let's do second context geometry. And now you can see all these guides turns on, which show that they are actually setting. And they are a bit big now, so let's go into the guide options and put these to 0.1. And here are our agents with our constraints. So if I haven't made a mistake, they should just fall down into ragdoll. And yes, like so. Cool. And just as a side note, you remember that we put up the transform group before, so we can use that in here if we would want to. So if I go here and if I set this to partial ragdoll, and then set the arm again, which was that group, and then take a clip, which is a walk, you can see that we now have this left arm flapping in ragdoll mode, even though we are playing the clip. Pretty cool if you ask me. Okay, so, but I don't want this. I want to have one ragdoll state, and I want to have one walking state. Let's turn this partial ragdoll off, and then also create a new state. And this state will be called walk. And I'm gonna merge these two together. Like so. And I'm going to just select this to walk. If you've seen my first course, you know that I like to use locomotion and not in-place animation, and also set up foot planting and clip properties. I don't want to rehash that here though, so if you want to know more about that, check that course out. But I don't want them to start in ragdoll either, so let's go into here and then select the walk instead. And I can select it here now because the state has the same name as a clip. Otherwise you need to type in the state name. So now we have a simulation of these guys, and they are ready to be triggered into ragdolls. I just realized I forgot to do something, and that is to go to the cone twist constraint and check this disable collisions, which means that the collision shapes that are constrained together won't collide with each other. Okay, so the next step is to trigger these guys into ragdoll when they get hit by a bullet. How would you do that? One way would be to measure how far a bullet is from an agent, and if it's close enough, that will trigger him. The problem is that the bullets are going so fast from one frame to another, and the bullet might have gone through an agent between two frames, but it won't be an actual frame where the bullet is close to him. So what I'm going to do instead is that I'm going to take the point position, and then I'm going to raycast back to his previous position. And if any agents gets hit when I'm doing that, then I know that that agent is supposed to be in ragdoll. So to do this, I need to have a point position to raycast, and then of course I have the bullet position, and then to raycast backwards I'm going to use the velocity that I just need to do some modification to. So let's go into tracer fire. I'm going to drop down an attribute up here. I'm going to select that guy. Let us just visualize the velocity first. So I'm going to click X and click on this velocity here, and in here I'm going to set this to marker and then to vector. And if we look at this, we have these very long vectors. The reason for that is that velocity is in seconds, so it's how far this particle will travel within a second. But when we are raycasting backwards, we just care about one frame. So what you need to do then is we need to divide one with whatever frame rate that we have. In this case, it's 24 frames per second. So if I do a constant 1, and another constant 24, and divide this, we get this fraction that we can multiply the velocity with. If you're multiplying a vector with a float, that will drive the length of the vector. So if I would, for example, multiply it by 0.5, the magnitude of that vector would be half of what it was before. If I do this here, multiply in here, you can see that suddenly I have much shorter vectors. Now you just get the length that is travel each frame. We still need to do a final thing though, because this is of course going forward. We want it to be pointing backward. Luckily it's really easy to do with vectors, so the only thing you need to do to reverse a vector is to multiply it by -1. Let's drop down another constant and set this to -1, and voila, now it's pointing backwards. Cool. So let's export this value out. So I'm gonna drop down a bind export, and I'm gonna set this to vector, and then I am going to call this ray direction. Right, let's go to the agents. So if we go into the crowd simulation here, I'm going to drop down the subsolver, and I'm going to connect that into the multisolver here at the end. The subsolver lets you do sub operations within a DOPSIM. Here we are in the subsolver, and now we just need to get the bullets into the simulation, so let's drop down an object merge. And then I'm going to point to the tracer fire. So here are our bullets, and then going to drop down an attribute up here. So here is our attribute VOP, and I'm going to connect the agents to the first port, so that means that this will iterate over the agents, and then I'm going to put the bullets into the second port. But in this case, we also want to iterate over the bullets. It's good that we iterate over the agents, but also for each agent, we want to iterate over the bullets and see does it hit me, and if it does hit me, then we're going to trigger it into ragdoll. So a way we can do this is to use a for loop. So if we drop down a for loop, and in a for loop you can specify a length, and then it will iterate that many times. Another thing you can do with it is you can put a value in here, and then you can modify that value and get it out here, and then it will remember that value over the next iteration, which is very handy. So what should we use for length? Well, we want to loop over each bullet, so let's count the bullets, and we can use that with a point count. And I'm going to take the second input here, because as you remember, here is our bullet coming in, and then I'm going to set this to the length. Great, so now we have one loop for each bullet, so let's do an intersect, which is a raycast. So before moving on, let us just talk about the intersect node. So I have this little setup here. I have a point, and then I'm raycasting down on this grid when it intersects. So if we go into this attribute VOP, we see I have an intersect, and I'm using the point position as a ray origin, and I also have a ray direction, and that is -1. One thing with intersect that is different from a ray node is that this ray direction is actually the length as well. So if I would go and move this, now it's 0.7, if I would move this over 1 like this, then suddenly it doesn't intersect anymore. If I would go in here and change this to -2 for example, then the actual ray is long enough again. So what you get from the intersect node then, you get the position where it intersects, and you also get a primitive number and a UV. And the primitive number would be the polygon that you are hitting. If you are hitting an agent primitive, then this prim number will be the number of the agent, and you won't get a UV anymore. So okay, let's go back. And we want to intersect with agents, which are in the first port here. And then we need a ray position and a ray direction. Let's import those. If we take import point attribute, by default is for point position here, so let's use that first. I'll get the points from the second input, which is what the bullets are connected to. For the point number, let us use the index number that will count up for every iteration. As we know that there will be as many iterations as points, this will give us every point number. And then let's put that into the ray org. Then we need one for the direction. So let's use this ray direction that we created before. And then connect that into the second port here. So cool. Now we have something that's go through each agent and each bullet and see if there is any intersections. If there is an intersection, we're going to get the primitive number of the agent that gets hit. So in that way, we know that if the current primitive number is equal to this one, then it's hit. So let's do a compare here and compare the primitive number. And now I'm going to compare it with the point number. Let's make a two-way switch here. So if it's getting hit, we want it to be set to 1. So I'm going to drop down a constant here. I'm going to set to 1 and put that in here, the top one, which is true. And then I'm going to plug that into the end here because we want to write out that value. And as you might recall, like I said in the beginning, this value that I'm setting here will be remembered. So I'm going to set a constant here, and then I'm going to start on 0. And because this starts on 0, if this is false, I want it to be 0. But it might be in the case that it's been hit by another bullet. Then I don't want to erase that value. But the good thing is that if I'm using this value here, and just connect this here, it will start being 0, because that is its start value. But if this is set to 1 here later, it will remember that for the next iteration. So if it's just set to 1 once, then the output here will be 1. Let's bind export that out. If this is 1, it means that the agent has been hit. So let's call that hit. And then go out to the DOPNet. And here in the DOPNet, I'm going to drop down a trigger, a crowd trigger, and a crowd transition. And I'm going to connect that into this last port in the crowd solver, as you might remember. In the crowd transition, I'm going to have walk to ragdoll. And here in the crowd trigger, you're going to use particle attribute lookup, so like so. And I'm going to use the attribute hit that I just created. And if this is equal to 1, then I know these guys are in ragdoll. So let's go out and check this. Let's go back and just turn off this visualizer, like so. And then I'm going to select the end of the chain here. And if we play this, there should be some guys falling over. Yeah, it seems to work. Cool, so this is a good start, but we're gonna improve it further. I'm out of the crowd sim and just looking at the one agent again. And we look at this clip here, we can see that we have an obvious problem here. So one way we can get around this is to use clip properties. And clip properties allow you to loop a specified frame range within a clip. So let's drop down a clip property. So I'm gonna create a new clip property here, and I'm gonna select the long jumps. So here's the clip, and then here I can set loop range. And if we look at the clip, it looks like 1, 2, 67 maybe. So let's put 67 there. And it's always nice to have a little bit of a blend when you are looping, so you don't get a very harsh transition. As you can see, this is not traveling with the agent, it's actually on a second branch. And I'm going to drop down a null here. Out properties. And if I look at it, I don't have anything. I just have this point here. And that is exactly what you get from clip properties. You get for every clip properties you add here. So if I add another one, and then we say short jumps, you can see now I have 2 points, 2 clip properties. I'm not going to remove that. So it's just a point with some attributes on. And then these attributes, they get read by the crowd solver. And you have these clip properties in the crowd object. So I can point to these. So where out properties. And as soon as you do that, it starts using these clip properties. But I'm actually not going to check it in this sim. I'm going to use another thing. This little helper node that Side Effects has created. So it's test simulation crowd transition. And if you take this one and then put the agent in the first port, and then the clip properties are at the last port. So I'm going to plug them in there. And then let's see. Now it's crazy because it doesn't know what to do. So I'm just going to select the long jumps. So now the long jumps clips is selected, and then it's going to use this clip properties because it's in the fourth port. So let's see how that looks. And you can see it's a little bit better, but it's not great, because if you see the foot, it's sliding all over the place. You don't get the harsh jump that you got before, but still this is not very good. So let's fix that. And how could you fix that? A way you can fix that is to use foot planting. The concept of foot planting is that with your clip you have these extra channels who tells you if the foot is supposed to be locked to its current position or if it's in the air. So how do you do this then? Because we don't have any foot plant channels currently. One way to get them in the clip is to add them with an agent prep and then write that out to the B clip. So let's drop down an agent prep. And by the way, what I do here, I could just do it on the fly after we imported the agent with its clip over here. But it's of course much nicer to have it baked into the clip in the first place. So I'm dropping down the agent clip here for the long jumps. And the agent prep, we're going to talk more about that later. But for now, the only thing I want with this here is to go to this second tab, additional channels. And then if I click this create footplant chop network, it's creating this chop network. And if we go into this chop network, what it's basically doing is taking all the animation curve from the current clip, and then it just pipes them out again. So if we go to the motion FX view and look here, here are all the animation curves in the clip. But what you can do, because it's writing out whatever you have here, so you can add stuff here. So you can add channels to this now. And I'm just going to set it up so we can see it a little better. So let's select that one, scene view. I'm going to pin this. I'm going to do a split left right. On this one, I'm going to put up a motion FX view. So now we're back here. So there is a chop node that you can use called footplant. So what this footplant does, it has a method to measuring if a joint is planted or not. First, there's two joints we need to care about. It's the ankle and the toe. So I'm gonna start with the ankle, and then I'm gonna plug this in here. I'm gonna look at this input source, and I'm gonna use agent, and I'm gonna point at that agent. So it's the long jumps. So like so. So if we turn these guys off and turn this guy on now, and also we need to go to the clip name and change that to long jumps. And then I want to have the ankle, so I'm gonna choose the ankle. So we get this curve. what does this tell us? We can actually see if I click this little icon here, then I get it synced with animations. I can see where I'm at. So if we look at the animation, you can see here it's planted. It's correct. This is 1, so which means that it's planted. And then if it goes and here's liftoffs and it's in there, you can see it's 0, so it's not planted. So this is doing what we want it to do. And how can it do this? Is because it's using this speed threshold. So if the speed is too low, then it's assumed that, right, it's not moving, it must be planted. And if it's higher, then it's like, oh, now it's something happened, it's moving, it's not planted anymore. This is actually the best method I found. Most of the time this works. Sometimes you can use the other one that is distant from terrain, and then if you do that, you can either have a terrain that you just point, you have this subpath that you can point it to, or you can just have a plane, and then you have a distance threshold instead, and that is using if it's close to the ground, it's under that threshold, then it would be planted, and if it's over the threshold, it's considered not to be planted. I'm going to go back to the speed threshold, and here the blend in frames and blend out frames. It depends on the clips, what kind of values you want here. The whole reason you want to have blend frames is that if you have an uneven terrain, it might be that the foot is locked, and then when it gets unlocked, it snaps back to its original clip position. It's a bit off, and therefore you want to have an interpolation between these two positions. But it depends. Sometimes you don't need much, and when you have a run, for instance, you don't need much, and when you have a slow walk, you need more. But anyway, so here is ankle, and we have to have a channel name, so I'm going to call this ankle planted. And then I'm going to copy this, and this is going to be the toe. And everything here is correct except this one. That's going to be toe instead. And then I'm gonna leave this, but I'm gonna have toe planted. So perfect. So if we go out here again and to this agent prep, to read this back now, we need to go here and click reload clips. So now we should have these extra channels. So if we go and write these guys out, gonna reload, and now I'm gonna need to drop down an agent prep again. And as I said from before, if you would just temporarily do it on the fly, you could just do the same thing that we just did in here instead, and then set the rest up here. But this is much better because now we already have the channels. What we need to specify now are the lower limbs, and that is just because Houdini needs to know what's going to be part of the IK chain. So let's add that, and obviously we don't have any left and rights, we just have one. But so for the upper leg I'm going to use thigh, and I'm going to use calf for the knee, and then I'm going to use ankle and toe, like so. And then I'm going to select the channels. So it's ankle plant channel, we have this ankle planted, and toe plant channel, we have toe planted. So perfect. Alright, so let's see what this did to our crowd test sim. So we have this. I need to go into terrain here, click enable footlocking. We don't need any terrain, footlocking works anyway. So if we see, it looks much better, and I'm gonna show that by copying this, and I'm gonna unselect this here. There's no foot planting here. Put the transform, merge, move that back a little bit, like so. And if we look at the difference, you see this one without foot locking, it's make this little wobble, and the other one stays planted. So much better.